Hi everybody, I'm Chris from FlipMath and I'm going to take you through another video, the third in a series on differentiation, and this one I'm calling To the Max. It's an AS module, part of the C1 module of the A-level course, and as usual I'll be teaching from a SEER perspective, but it should be applicable to all boards. The objectives of today's lesson: define what a turning point is and what happens there, find the coordinates of stationary points, given that stationary points is another word for a turning point, and how to tell whether the turning point in question is a maximum or minimum. All of which may not make any sense to you at the moment, but hopefully should be a little more clear come the end. We're going back to the park. In our last video, I took you through how, or in the first video actually, how differentiation talks about the story of movement. So what happens is it changes places, it changes pace and speed and pitch and trajectory and all those things. And it explained it by talking about an amusement park or a roller coaster in an amusement park. So we're going to go back to the roller coaster itself. What happens at this point up here at the top? When you reach the top of the roller coaster just after ascent, a couple of interesting things happen. You come to the verge, you're just on the verge of changing direction or reaching what we'll call a turning point. So you're going up on the ascent here, and just after you get to this point, you're going to end up going down again, usually very fast in a roller coaster. You go whee, throw your hands up. Well, veterans of roller coasters do anyway. At the end of the ascent, you come to a near standstill, what we call coming to rest on mechanics. So it's just to get to the top. They do it in roller coasters mainly to build tension just before the fall, so that you tip over ever so slowly and go down. But you also, are conserving energy as well. So you don't want to be really carrying too much speed to going down, because it means that you'll go that much faster on the way down, and that may be dangerous. We'll study that more in mechanics though. As soon as you start to go down the other side, we'll pick up speed again. We also call this point up at the top, up here, a stationary point. So turning point because you're changing direction, and stationary because you generally are coming to a stop. If I were to draw a tangent at this point at the top, what would it look like? I'm going to get rid of the dot and get rid of the text there. And I'll draw a tangent. It's just a straight line that goes across. Do you know what the gradient of that line is? Well, if you go back to your GCSE idea of gradient is the change in y divided by the change in x, or the y is overrun, or y2 minus y1 over x2 minus x1, we can see that the change in going up or down is 0. Therefore, 0 divided by anything gives us 0. So the gradient of that line is 0. Another reason we call it a stationary point is because the gradient is 0, something equals 0, stationary. The main point of this is to say that at a turning point or stationary point, dy by dx, or the gradient function, is equal to 0. And this is very helpful when solving and trying to find where the stationary points are. So now that we know the theory, we'll examine how to find the coordinates of some turning points. So our objective is to find the coordinates of the turning point of a curve. Why is this important? Well, it's part of the 6-week assignment, so you can start thinking or researching this about why this is necessarily important. Turning point. Okay, so here is a curve. It's actually a quadratic graph. How many turning points are there on this graph? So we're coming up along here, round and round, and away we go again. Well, there's one there. We'll turn and change direction there, and we'll turn and change direction there. So there are 2. The equation of this line is 2x cubed minus 3x squared plus 1. And we're going to see the coordinates of the turn. So we could just see the coordinates of the turning points rather, just by reading them off. You can see the coordinates of that turning point are 0, 1, and of that one down there are 1, 0. So we're going to calculate them, and we'll see if we get exactly that. So stick with the same objective, and we'll work through. So find the turning points of the curve y equals 2x cubed minus 3x squared plus 1. We know from the roller coaster investigation earlier on that turning points occur when the gradient function is equal to 0. And how do we get the gradient function? Going back to the first of our lessons and the second of our lessons, the gradient function we get by differentiating. And we're going to differentiate our curve expression up above. When we do that, we're going to get 2 times 3 gives us 6, and let's decrease the power of x here by 1, that gives us 6x squared. Then minus 3 times 2 gives us minus 6. 2 minus 1 gives us 1, so it becomes x. And when we differentiate a number or constant term, it disappears. We're going to solve this equal to 0. So that would be 6x squared minus 6x equals to 0. And it's very common for people just to go, well, I'll move the minus 6x over to the other side, and then one of my x's will cancel out. That is not how you should solve this problem. When you've got it equal to 0 like this, you should take out common factors. So what are both have in common? I normally preach the sign, number, letter theory. So what signs can take out, not really applicable here. Numbers. What numbers? That's a common factor of 6 and 6. True enough, it's 6. And what letters have they got in common? Well, they've got 1x in common. So I'm going to take 6x out as a factor. And if I divide both terms left there by 6x, 6x squared divided by 6x will leave me x. And minus 6x divided by 6x gives me 1. So we get 6x upon x minus 1 equals 0. And I can solve both of those points equal to 0. So if 6x equals 0, gives us x equal to 0, and then x minus 1 equal to 0, rearranging gives us x equal to 1. So the x-coordinates of our two turning points are 0 and 1. We must find the corresponding y-coordinate for each x value. And just like before, remember that the relationship between y and x is given by the original curve. The dy by dx is just the gradient function. So if I want to find out what y is when we know x, I substitute the x value into the original equation up here. So putting x equals 0 into y equals 2x cubed minus 3x squared plus 1. Substituting, you can see I've replaced the x's with a 0, plug it all in, and I'll get that y is equal to 1. And if I do the same for 1, we'll get 2 times 1 cubed minus 3 times 1 squared plus 1. That's 2 minus 3 plus 1 gives me 0. So when x is equal to 0, y is equal to 1. And when x is equal to 1, y is equal to 0. This gives us the turning points 0, 1 and 1, 0, just as expected from before. And we've calculated them. Success! Hooray! I've even put in a hashtag for backslapping all round. It all worked out fine. Remember, if you had have rearranged up here slightly incorrectly with moving the minus 6x over to the right and cancelling out an x, you wouldn't have got your x equal to 0 turning point. And that's why factorizing like that is very important. You'll see this coming up a lot in past papers, but if you're unsure, give me a shout. Is this the end of the turning point story? Well, of course not. There's one slightly, not difficult, but there's one more step to go, or another thing we can tell from our calculations. So we're going to define our points. I've drawn a little diagram here. So if you've got a hump that goes up and then round and down, we call that a maximum. So we're talking about these points. So you're at the top of the hill. So it's the highest point you can be. And the minimum is when you're going into the valley. So you're getting down to the very lowest point. So it's the minimum. Now the negative and positive bits that I've put around is what the gradients are. So the gradient that runs from left to right and rises is will be a positive gradient. And one that goes left to right but sinks is a negative gradient. So it goes positive, then the gradient is 0, and then negative, and then a negative, 0, and positive. And one of the ways you can do this is by substituting values in your gradient function just before the x value of your turning point and just after, and read the gradients off whether they're positive or negative. So we are going to define, or going to be able to define, whether something is positive or negative. And like I said before, we could find the gradient just before that value that we've got for the turning point, and just after, and compare them like I've just pointed out. However, this is really important when it comes to solving real life problems, because when we use differentiation to find things out, we're really trying to find optimal solutions. So in a curve, it's easy to find by the highest point in the curve and lowest point of the curve what we call the maximum efficiency of doing something and the minimum efficiency. And we'll see some examples coming up uh, in the next lesson, which what I call in real life, differentiation in real life. So it's pretty important to know whether you're giving somebody the worst way to do something or the absolute best. So if you find two turning points or 2 points where they change direction, you want to be able to tell them, we'll do it this way and not this way, because that one gives the maximum solution and that one gives the minimum. Maximum is when it rises up the top and the minimum is when it's at the bottom. I'm going to introduce an idea called the second derivative. And thankfully the second derivative gives us an easier way to do this than comparing gradients the whole way through. It's called the second derivative and tells how the slope changes as we increase our x value. So the second derivative is basically what happens when you differentiate again. So you take your gradient function and differentiate that. So it tells us how the slope changes as we increase our x value. So if you look at a maximum point, as it changes and gets past the stationary point, it becomes a negative. Maximum points change into negative gradients. Similarly, minimum points change into positive gradients. So, like I said before, if dy by dx is the first derivative, we write the second derivative as d2y by dx squared. It's a bit of a funny looking animal, but you'll get used to writing it, much like anything else. And if you're in class, I'll take you through some common mistakes that are made with this kind of thing. But it's the notation for the second derivative. When you're doing your calculation and you substitute your values in, as you'll see in a second, if this second derivative is a plus, that means that it's a minimum point. And if the d2y by dx squared is minus, that means it's a maximum point, because it's about what type of gradient it's turning into at that point. You know, is it becoming negative or is it becoming positive? It's counterintuitive, but again, with a little bit of practice, you start to think no more of it. So let's put it into practice. Let's find the nature of turning points, whether they're maximum or minimum. An example, we'll look at the example we were doing earlier, because I just like to do those kind of things. So this was, we could see that 0, 1 was a maximum and 1, 0 was a minimum from before. And let's check to see if that maths works out. Our expression for the first derivative was dy by dx equals 6x squared minus 6x from earlier. If we differentiate that again, we'll do 6 times 2 gives us 12, and then 2 minus 1 gives us 1, so we'll get 12x, and then when we differentiate minus 6x, we get minus 6. We're going to substitute in our values, our x values in here. So we're going to substitute in x equal to 0, so that'll give us 12 times 0 minus 6 gives us minus 6. So when x equals 0, that gives us a negative value. When we do the same with x equal to 1, we get 12 times 1 minus 6, which gives us plus 6, which is a positive value. And if you remember back, negative values mean that that turning point is a maximum. So there's a maximum at 0, 1. Sure enough, that's correct. And positive values mean a minimum turning point at 1, 0. And sure enough, that is correct. Let's put it all together in one final example. So we're going to find the coordinates of the turning points of the curve y equals 3x cubed minus 4x plus 3 and determine their nature. And this phrase, determine their nature, comes or means that you're going to work out whether they're maximum or minimum and define them. So you're not just going to give the coordinates, you're going to say whether they're maximum or minimum, even without drawing or sketching the graph yourself. Remember, sketching or checking in Desmos or something similar to that can be very beneficial in helping you, but you don't actually need it as it turns out, but it's good for checking your work. So we've been given the curve y equals 3x cubed minus 4x plus 3, and we'll get the turning points by solving the derivative dy by dx equal to 0, because stationary points or turning points happen when the gradient is equal to 0. When I differentiate that, I'll get 9x squared minus 4, and I'm going to solve that. I'll get x squared equals 4 over 9, And that will give me x equals plus or minus 2 over 3. Remember, when you take the square root of a number, you get positive and negative values. And there are 2 turning points, sure enough. This gives our turning points x values to be 2 plus 2/3 and minus 2/3. We need to get the y coordinates. And where do we substitute the x values in to get the y coordinates? That is correct. The original expression curve tells us the relationship between y and x, not dy by dx, because that's just the gradient function. It gives us a definition for finding the gradient. So we must find the y coordinates still and their nature. We'll do the y coordinates first. We'll substitute x equal to 2/3 into the curve. I've shown you how to do it or what to type into your calculator. So I'm going to replace the x by the 2/3, cube it, and then times it by 3. Take away 4 times the 2/3 plus 3, and that gives us 11 over 9, which works out to be 1.222222, repeating decimal. If you want to turn it into a decimal for plotting or checking your sketch graph. If I sub x equal to minus 2/3 in, I get plus 43 over 9, which is 4.778. Well, it's actually 77777, recurrent decimal as well, but we rounded it to three decimal places there. Okay, so that gives us our turning points to be 2 and 11 over 9, and minus 2/3, 43 over 9. The last thing we must do is determine whether each point is a maximum or minimum. We do this by working out our second derivative. So we're going to take our first derivative, our dy by dx, and we're going to differentiate it again to give 2y by dx squared, and that'll be 2 times 9, which gives us 18x. The minus 4 disappears. Substitute in each of our x values. In many cases, you don't even need to work out what the actual value is. You are only interested in the sign. So you're going to do 18 times 2/3. That's a positive times a positive. So it's going to give a positive. Therefore, that turning point is a minimum at 2/3. And 18 times minus 2/3 is a positive and a negative. That's going to give a negative value, therefore a maximum. And the answer is 2/3, 11 over 9 is a minimum, and minus 2/3 and 43 over 9 is going to be a maximum. We're going to check to see if this does make sense. So our answers we found before were 2/3 and 11 over 9 was a minimum point, and minus 2/3 and 43 over 9 is a maximum. And if I show you the graph plotted in Desmos, sure enough you can see that the minus 2/3 and 4.778 is a maximum, and the 0.6671222 was a minimum. Next time, we're going to look at techniques, use all the techniques learned so far to find optimal solutions to real-life problems, and examine techniques in building algebraic expressions. Our objectives were to define what a turning point was and what happens there, find the coordinates of stationary points, and how to tell whether the turning point is a maximum or a minimum. And there's my obligatory spelling mistake or typo, because I don't really think it's a spelling mistake. I don't actually think this and thought point was point. So we'll knock that out. And I think we met all three. If you're not sure whether we did, send me some tweet at flipmath or comment in the video below. Do fine. Practice, practice, practice. For exercises, solutions, quizzes, and downloads around the subject, go to flipmath.co.uk and search for differentiation. Down the bottom of the front page, down at the bottom, go to the search box and type in differentiation. Feedback on all resources should be sent to @flipmath. Any glaring errors, I would be very grateful for you to point out to me. And like, comment, subscribe to the video, and I'll catch you next time. Bye.